If you close your eyes and picture energy, you probably imagine some kind of glowing blue fluid, or a crackling lightning bolt, or maybe a shimmering aura that flows from a battery into a light bulb. You think of it as a stuff, a substance, a blob of something that moves from place to place. I hate to be the one to ruin the magic trick, but that is completely wrong. In physics, today, right now, we have no knowledge of what energy is. We do not have a picture that energy comes in little blobs of a definite amount. It is not a fluid, it is not a gas, it is not a ghost inside the machine. So what is it? It is a number. That's it. It is a mathematical quantity. It is an abstract bookkeeping rule that nature, for some reason, decides to obey. Here is the situation. There is a fact, or if you wish, a law, governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know. We call it the conservation of energy. It states that there is a certain numerical quantity, which we call energy, that does not change in the manifold changes which nature undergoes. That is a most abstract idea, because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It is just a strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it is the same. Imagine a bishop on a chessboard. If you look at the red squares, the bishop is always on a red square. You can move it, you can dance it around, you can distract it. But if you count the number of bishops on red squares, that number is conserved. Energy is like that. It is a rule of the game, not a piece on the board. To understand this, we have to stop thinking like physicists and start thinking like a mother dealing with a very mischievous child. Imagine a child. Let's call him Dennis, the menace. Dennis has a set of blocks. These blocks are absolutely indestructible and cannot be divided into pieces. Each is the same as the other. Let us suppose that he has 28 blocks. His mother puts him with his 28 blocks into a room at the beginning of the day. At the end of the day, being curious, she counts the blocks very carefully. She discovers a phenomenal law. No matter what he does with the blocks, there are always 28 remaining. This continues for a number of days, until one day there are only 27 blocks. Now, does she assume the law of conservation of blocks is broken? No. She investigates. A little looking around shows that there is one under the rug. She must look everywhere to be sure that the number of blocks has not changed. One day, however, the number appears to change. There are only 26 blocks. Careful investigation indicates that the window was open, and upon looking outside, the other 2 blocks are found. The accounting works. The number is saved. Another day, careful count indicates that there are 30 blocks. This causes considerable consternation until it is realized that a neighbor boy came to visit, bringing his blocks with him, and he left a few at Dennis's house. After she has disposed of the extra blocks, she closes the window, does not let the neighbor in, and then everything is going along all right, until one time she counts and finds only 25 blocks. This is where it gets interesting. There is a box in the room, a toy box, and the mother goes to open the toy box, but the boy screams and says she is not allowed to open it. So now she has a problem. She has 25 visible blocks. She is missing 3. She suspects they are in the box, but she cannot see them. The energy is hidden. Being extremely curious and somewhat ingenious, she invents a scheme. She knows that a block weighs 3 ounces, so she weighs the box at a time when she sees 28 blocks, and it weighs 16 ounces. The next time she wishes to check, she weighs the box again, subtracts 16 ounces, and divides by 3. She discovers a formula. The number of blocks seen plus the weight of the box minus 16 ounces divided by 3 ounces equals a constant. In the graduate, there then appear to be some new deviations. Careful study indicates that the dirty water in the bathtub is changing its level. The child is throwing blocks into the water, and she cannot see them because it is so dirty. But she can find out how many blocks are in the water by adding another term to her formula. Since the original height of the water was 6 inches, and each block raises the water a quarter of an inch, this new formula would be the number of blocks seen plus the weight calculation of the box plus the height of the water minus 6 inches divided by a quarter inch equals the constant, 28. In the gradual increase in the complexity of her world, she finds a whole series of terms representing ways of calculating how many blocks are in places where she is not allowed to look. As a result, she finds a complex formula, a quantity which has to be computed, which always stays the same in her situation. Now, what is the analogy of this to the conservation of energy? The most remarkable aspect that must be abstracted from this picture is that there are no blocks. Take away the first terms in our equations, and we find ourselves calculating more or less abstract things. The analogy has the following points. First, when we are calculating the energy, sometimes some of it leaves the system and goes away, or sometimes some comes in. In order to verify the conservation of energy, we must be careful that we have not put any in or taken any out. Second, the energy has a large number of different forms, and there is a formula for each one. These are gravitational energy, kinetic energy, heat energy, elastic energy, electrical energy, chemical energy, radiant energy, nuclear energy, mass energy. If we total up the formulas for each of these contributions, it will not change except for energy going in and out. But remember, there are no blocks. We don't know what the mechanism is. We just know that if we take the speed of a car and square it and multiply by the mass and divide by 2, we get a number. And if we take the height of a rock and multiply by the weight, we get another number. And if we measure the temperature of a radiator, we get another number. And when we add all these seemingly unrelated numbers together, the total stays constant. It is an abstract thing in that it does not tell us the mechanism or the reasons for the various formulas. It just works. Conservation of energy can be understood only if we have the formula for all of its forms. Let's start with the simplest one, gravitational energy near the surface of the Earth. I wish to derive this formula in a way which has nothing to do with history, but is simply a line of reasoning to give you an illustration of the remarkable fact that a great deal about nature can be extracted from a few facts and close reasoning. Consider weightlifting machines, machines which have the property that they lift one weight by lowering another. Let us also make a hypothesis that there is no such thing as perpetual motion with these weightlifting machines. That is, if we have lifted and lowered a lot of weights and restored the machine to the original condition, we find that the net result is to have lifted a weight. Then we have a perpetual motion machine because we can use that lifted weight to run something else. We assume this is impossible. If you could build a machine that lifts a heavy weight by dropping a light weight a short distance and then resets itself without using fuel, you would be a billionaire. But nature is stingy. She doesn't allow it. Imagine a very simple weightlifting machine, a lever or a pulley. This machine lifts weights 3 units strong. We place 3 units on one balance pan and 1 unit on the other. However, in order to get it actually to work, we must lift the little weight off the left pan. On the other hand, we could lift the 1 unit weight by lowering the 3 unit weight, if we cheat a little by lifting a little weight off the other pan.
Of course, we realize that with any actual lifting machine, we must add a little extra to get it to run. This we disregard temporarily.
Ideal machines, although they do not exist, do not require anything extra. A machine that we actually use can be, in a sense, almost reversible. That is, if it will lift the weight of 3 by lowering a weight of 1, then it will also lift nearly the weight of 1, the same amount, by lowering the weight of 3. We imagine that there are 2 classes of machines, those that are not reversible, which includes all real machines, and those that are reversible, which of course are actually not attainable, no matter how careful we may be in our design of bearings and levers. We suppose, however, that there is such a thing, a reversible machine, which lowers 1 unit of weight by 1 unit of distance, and at the same time lifts a 3 unit weight. Call this reversible machine, Machine A. Suppose this particular reversible machine lifts the 3 unit weight a distance x. Then suppose we have another machine, Machine B, which is not necessarily reversible, which also lowers a unit weight a unit distance, but which lifts 3 units a distance y. we can now prove that y is not higher than x. That is, it is impossible to build a machine that will lift a weight any higher than it will be lifted by a reversible machine. Let us see why. Let us suppose that y were higher than x. We take a 1 unit weight and lower it 1 unit height with machine B, and that lifts the 3 unit weight up a distance y. Then we could lower the weight from y to x, obtaining free power, and use the reversible machine A running backwards to lower the 3 unit weight a distance x and lift the 1 unit weight by 1 unit height. This will put the 1 unit weight back where it was before and leave both machines ready to be used again. We would therefore have perpetual motion if y were higher than x, which we assumed was impossible. With those assumptions, we thus deduce that y is not higher than x, so that of all machines that can be designed, the reversible machine is the best. We can also see that all reversible machines must lift to exactly the same height. This is a very remarkable observation, because it permits us to analyze the height to which different machines are going to lift something without looking at the interior mechanism. We know at once that if somebody makes an enormously elaborate series of levers that lift 3 units a certain distance by lowering 1 unit by 1 unit distance, and we compare it with a simple lever which does the same thing and is fundamentally reversible, his machine will lift it no higher. So, what is this distance, x? Suppose we have a reversible machine which is going to lift this distance x, 3 for 1. We can prove by logic alone that x must be 1/3 of a foot. The generalization is clear. 1 pound falls a certain distance in operating a reversible machine, then the machine can lift a certain amount of pounds, this distance divided by that amount. Another way of putting the result is that 3 pounds times the height lifted, which in our problem was x, is equal to 1 pound times the distance lowered, which is 1 foot. If we take all the weights and multiply them by the heights at which they are now, above the floor, let the machine operate, and then multiply all the weights by all the heights again, there will be no change. We call the sum of the weights times the heights gravitational potential energy, the energy which an object has because of its relationship in space relative to the Earth. The formula for gravitational energy, then, so long as we are not too far from the Earth, is the weight times the height. It is a very beautiful line of reasoning. The only problem is that perhaps it is not true. After all, nature does not have to go along with our reasoning. For example, perhaps perpetual motion is, in fact, possible. Some of the assumptions may be wrong, or we may have made a mistake in reasoning, so it is always necessary to check. It turns out experimentally, in fact, to be true. The general name of energy, which has to do with location relative to something else, is called potential energy. In this particular case, of course, we call it gravitational potential energy. If it is a question of electrical forces against which we are working, instead of gravitational forces, if we are lifting charges away from other charges with a lot of levers, then the energy content is called electrical potential energy. The general principle is that the change in the energy is the force times the distance that the force is pushed. But this is just the beginning. We have only talked about statics, things standing still. What happens when things move? Where does the potential energy go when a pendulum swings down to the bottom? The gravitational energy disappears when it is down at the bottom. Nevertheless, it will climb up again. The gravitational energy must have gone into another form. Evidently, it is by virtue of its motion that it is able to climb up again. So we have the conversion of gravitational energy into some other form when it reaches the bottom. We call this kinetic energy. And just like with the blocks, we need a formula for it. We need to find where the blocks are hiding when the object is moving. And trust me, the formula for motion is where things start to get really messy. We left off with a nice, tidy picture of the universe. We had weights and heights. We had reversible machines. We established that if you lift the rock, you are storing a number, gravitational potential energy. But the universe refuses to sit still. What happens when you drop the rock? As it falls, it loses height. The gravitational potential energy is vanishing. The number on our balance sheet is dropping towards 0. If the law of conservation of energy is real, if those indestructible blocks haven't simply ceased to exist, they must have gone somewhere. They must be hiding. Look at the rock just before it hits the ground. It has no height left, but it has something else. It has speed. It has motion. If we attach that moving rock to a rope and a pulley system, its motion can pull another weight up. It has the capacity to do work. The energy didn't disappear. It shape-shifted. It turned into kinetic energy. Now we need a formula for this. We need to know how many blocks are hidden in a moving object. Recall our arguments about reversible machines. We can see that the motion at the bottom must correspond to a quantity of energy that permits the object to rise back to a certain height. It doesn't matter how it got that speed, whether it fell from a cliff, was shot from a cannon, or was pushed by a rocket. Motion is motion. When we do the math, we find a specific rule. To find the kinetic energy, you take the weight of the object, multiply it by the square of its velocity, and divide by a constant related to gravity. Notice that's squared. That is critical. If a car goes twice as fast, it doesn't have twice the energy, it has 4 times the energy. This is why high-speed impacts are so much more violent than low-speed ones. The number of hidden blocks explodes as you go faster. So now we have 2 places to hide our blocks. In height, potential, and in speed, kinetic. Is that it? Is the universe just things going up and down and fast and slow? Of course not. Nature is far more devious than that. Consider a spring. If you pull down on a spring, you are doing work. You are sweating, pulling against the metal. You hold it there. The spring isn't moving, so there is no kinetic energy. It hasn't changed height, so there is no gravitational energy. Yet you know there is energy there. If you let go, it snaps back. It can lift weights. It can smack you in the face. We have to invent a new term, elastic potential energy. This is the energy stored in the tension of the spring. But wait, there is a problem, a flaw in our beautiful reversible machine logic. We cheated. Throughout this entire explanation, we have been assuming that machines go on forever. We assume that a pendulum swings back up to exactly the same height it started from. We assume the spring bounces forever.
But you know that's a lie. If you swing a pendulum, eventually it stops. If you bounce a spring, eventually it settles down. When the pendulum stops, it has no height. It has no speed. The potential energy is 0. The kinetic energy is 0. The numbers are gone. Did the blocks disappear? Did nature finally break the law? Where did the energy go? This brings us to the most brilliant hiding spot of all. Heat. Inside the spring, inside the pendulum, inside the air they move through, there are crystals and molecules made of billions of atoms. When things move on a large scale, like a car rolling or a pendulum swinging, we try to be very delicate. But nature is messy. There is friction. There is bumping. As the motion slows down, the visible kinetic energy disappears, but the invisible kinetic energy appears. The atoms inside the material start to jiggle. They start to wiggle in a random, confused manner. We lose track of the energy on the macroscopic scale, but it is still there. If you put a sensitive thermometer on a spring that has just stopped bouncing, you will find it is warmer. That warmth is the energy. Heat energy is not a new thing. It is just kinetic energy, internal motion, hidden in the chaos of the crowd. This is a profound realization. It means that what we call heat is just the kinetic energy of atoms that are too small to see. The blocks didn't vanish. They just got chopped up into dust and scattered among the atoms. But if you could count the motion of every single atom, the total number would still be exactly the same. Once you accept that energy can hide in the jiggling of atoms, you start to see it everywhere. There is electrical energy. This has to do with pushing and pulling electric charges. There is radiant energy. This is light. We know light carries energy. It heats up the pavement. It burns your skin. Light is just a wiggling in the electromagnetic field. There is chemical energy. This is the energy released when gasoline burns or when you digest food.
But what is it really? It is just the electrical energy of atoms attracting and repelling each other. It's the same rules, just deep inside the chemistry. There is nuclear energy. This is the energy involved with the arrangement of particles inside the nucleus of an atom. We have formulas for it, but honestly, we don't fully understand the fundamental laws of it yet. And finally, there is the monster, the one discovered by Einstein, mass energy. It turns out that an object has energy simply from its sheer existence, even if it is sitting still at absolute zero temperature with no height and no electric charge. It has energy because it has mass. If you take a positron and an electron and you bring them together, they disappear, they annihilate, and out comes radiant energy, light. You can calculate exactly how much. The formula is the mass times the speed of light squared. This means mass and energy are the same thing. Mass is just a very, very dense way of storing the blocks. So, where does this leave us? We have a law, conservation of energy, that seems to be absolutely true. We check it in steam engines, in stars, in atoms, and in galaxies. The number always balances. The blocks are always found, whether under the rug, in the toy box, or in the jiggling of atoms. But remember what I said at the beginning. We don't know what energy is. We do not understand energy as counting little blobs. It is a mathematical quantity. It is abstract, and it gets stranger. In quantum mechanics, we learned that this conservation law is actually related to time. It turns out that conservation of energy is just the physicist's way of saying the laws of physics don't change depending on what time it is. If you do an experiment today and you do it again tomorrow, nature behaves the same way. That symmetry in time is what causes energy to be conserved. Energy is not a substance. It is the shadow cast by the consistency of reality. Before we finish, I have to give you a warning. I told you that energy is conserved. That implies we can never run out of it. So why do we worry about saving energy? Why do we pay electric bills? Because while energy is conserved, useful energy is not. There is a lot of jiggling around in the atoms of the sea. The ocean has a massive amount of heat energy, but you can't get those atoms to herd together and drive a ship unless you have a temperature difference, unless you take energy from somewhere else.
Nature doesn't care about us. She has conservation of energy, but she spends it in all directions. The sun liberates massive amounts of energy, but only a tiny fraction, 1 part in 2 billion, falls on the earth. The rest is lost to the void. Our job, the job of the physicist and the engineer, is to figure out how to catch those blocks before they get hidden under the rug of entropy. We get energy from the sun, from rain, which comes from the sun, from coal, which is stored sunlight, and from uranium. If we can figure out how to control thermonuclear reactions, fusion, we could get enough energy from 10 quarts of water per second to power the entire United States. It can be done. The blocks are there. We just need to be smart enough to find them. So the next time someone talks about energy, don't picture a glowing blue fluid. Picture a child hiding blocks. Picture a number that refuses to change. And remember that even though we can't touch it, and we don't really know what it is the one thing in this universe that we can count on.